Good afternoon. I think we just passed the Memorial Day long weekend, and usually, if I would like to do something for the long weekend, but this weekend is probably the most special Memorial Day holiday that I ever had. In a way that I just do what I did is just like the song that we played all by myself. So not sure how many of you are like me, like just by yourself, but uh, when you are by yourself, you're probably not going to like review the content that we have taught before. So that's why we still need to have some kind of a recap every time before we start, so that you know why we are here and where we are coming from. So we said that in modern digital circuit design, there are two types of a circuit. One is the combinational circuit and sequential circuit. However, most of the time, our design cannot just be accomplished with just one type of circuit. So instead, the circuit right now is like you have the sequential network um, that buffers the state from the previous result and use that as part of the input combined together with your current input and then drive the combinational circuit that you have in your design to make the whole function work. So, we learned because the flip-flops in sequential circuit, they require the clock signal to function correctly. And so it becomes really important that we have to decide what's the right period of time for the clock. And the clock period, the high level guideline, we will definitely have a lecture on more detail how to decide the clock cycle this Thursday. But before we go into that, the high level concept you have to keep in mind is that it must be longer than the longest delay from the state register's output to its input. So that's the critical path, right? And then we talk about that. Well, we have conventional circuits to implement those adders, and we also have serial adders. And the good thing about the serial adder is because between the registers, the critical path is shorter. So we see the frequency is longer. However, another thing that we later learned is that, well, even though the frequency is longer, however, the number of cycles that we have to go through and the total number of gate delays that we have to go through using serial adders is actually longer for each add operation. So that might not be a good deal if we use serial adders. So, however, a very important technique that is widely used in modern digital circuit design is the pipelining idea. So the basic idea of pipelining is that each part of the hardware component only perform part of the job for an operation, and then use those pipeline registers to buffer those intermediate results and propagate the intermediate result as the input of the next stage. And gradually, we will spend more cycles in finishing the same job. But what will really happen is that if you run a sufficient amount of jobs, then it turns out that the throughput, or say the average latency of completing a job, is just as long as your cycle time. So in this way, cycle time becomes correlated to your performance. So if you can shorter the cycle time of your combinational part of your circuit, and you can duplicate that as multiple copies or divide a job of an operation into multiple pieces and still maintain a high clock rate, then turns out that you can, if you have sufficient amount of jobs, then the average latency for completing each job, or the total latency of completing this huge amount of jobs, is going to be shorter than the giant combinational circuit. And we already demonstrate that in adders, and we do have some questions that you practiced before on adders. And then we also know that adding adder is not the only operation that we care about. So instead, so in addition, we talk about the multiplier. So for the multiplier, we also want to tell you what's the best way of making it efficient if it's a joint combinational circuit. And turns out this array style circuit is one of the best implementation. And if you estimate the number of gate delays, then you will figure out that for if you want to expand that to be a 32-bit, then you need a few 33 to 64-bit adders. And how to tell this is that if you look at the array style adder here, right? This is 4-bit, and then we need 5-bit, 6-bit, and 7-bit adder until we reach the end. So the same thing for 32-bit array style multipliers, because our final result could be as large as 64-bit. So so we need this number of adders. And if you remember what's the gate delay of a carrier lookup adder is basically n divided by 4, rounded up times 2 plus 1. And then you can figure out, well, this is the total amount of adders we need in implementing the multiplier. So it turns out that, well, the gate delay is around like 800, so it falls in this category. So that's where we end in the last lecture. So today we are going to talk about more multipliers, and then we are going to talk about high-level state machine, RTL design, and how to put everything together in design a simple multiprocessor, a microprocessor. So let's talk about the design of multipliers, more multipliers. So far we talk about the best one is the array style. However, there is a better design that you can potentially do. That's a parallel tree multiplier. So if you look at the so the basic idea, it's similar to carry look ahead in some sense, is that if we think about what we really care about in how we get each of the bit in the product, right? And you will figure out that for the product 0 to product 1, all you need is just the A0, B0, or some of the lower bits result from these adders. And for some of them, right, the middle part, you only need the result from the middle adder. So in this way, if I want to make a 32-bit multiplier, I can actually create a tree of 32-bit adders, and those 32-bit adders only capture the necessary part of my input to generate the result. So for example, like if I want to generate P0, it's basically A times B0 plus A times B1, and then if you add them together, then some part of it will go to your P0, some part of it will go to P1. And gradually, if you have sufficient amount of adders, and then you can make a tree of this, right? So apparently, for this kind of adder design, you need a lot more 32-bit adders than the previous one. So if you look at the array style, right? If you look at the array style, all you need is saying that, well, I have, so for this array style, I have, if it's a 32-bit one, right, all you need is, how many? You need 32 adders in total, right? However, for as you can see from here, right? However, if you want to make a tree, right? If you want to make them a tree, then every pair you will need quite a few adders. So again, right, we are always trading the area with efficiency. So if you are willing to put more gates in the adders, and what the latency would give you is that if you think about if you want to build a 32-bit tree of adders, right? A tree of adders, right? You need a total of 32 adders, and you are organizing them as a binary tree. So turns out that you only need 5 level of adders, and each of the adder, it has 19 gate delays. So the gate delays that you are suffering by using a parallel tree multiplier is less than 100 gate delays versus the A08 gate delays that we just learned from the array style that your textbook tells you, right? So parallel tree is actually one of the best multiplier implementation that you can find in combinational circuits. All right, so these are the combinational part. So for the combinational part, we have the traditional shift and add adders. We have the array style adders. And now I told you there is something called parallel tree multipliers, right? So, and parallel tree multiplier is the one consume the most area because we basically need 32-bit adders. And but because we organize this 32-bit adders as trees, so the efficient latency is only 5 levels of the carrier lookup ahead adder delays. So it's only about like 95 gate delays, which is 8 times better than the array style. So these are the adders that these are the multipliers that we learned so far. So how about sequential logic based multipliers? So let's go back to look at this, right? So if you look at the binary multiplication, right? Think about how you do the in decimal, and we have learned about this, right? If you remember how we deal with the sequential adder is that we are not too greedy, right? Every cycle we just generate the result for a bit. And similarly, for the binary multiplication, we are not too greedy in a way that every cycle we just gradually build up the partial result, or say the half-baked result of the multiplication. So the idea is that for the first cycle we generate a PP1, and the second cycle we generate a partial, and we call this like M0, M1. And the second cycle, we generate an M2, which is equivalent to PP1 plus PP2. And for the third cycle, we are generating something that's efficient, equivalent to PP1 plus PP2 plus PP3, right? And gradually we will build up the result. So that's our goal, right? So if that's our goal, then what would happen here is that you can say, well, essentially this is what you want to get. You want to get M equal to A times B. And in each of the cycle, we generate something called Mi plus 1. And so in cycle 0, we are generate M1, which is M0 plus 0. M0 is basically 0 plus like A times B0 times A 2 to the 0, which is actually the PP1. And then the second cycle, we are generating M2, which is the previous PP1 plus the PP2, right? So that's our goal. So if we want to design a circuit like this, right? The basic idea is probably we are going to produce a sequential circuit like this. So first of all, right, the input for every cycle is basically your multiplier, and for each multiplier, because this is the B, right? We only need the BI at each moment. So, and after you use the BI, you never want to reuse it. So let's shift it right, and let's take the last bit as the input, right? And because it's binary number, you can only have like 0 or 1, right? So if it's 1, you know what you want to do is that you just shift the current multiplicand left, because because by shifting left, you are doing 2 to the I, right? And then if it's 1, then we do we add the number. If it's 0, then you are adding 0. So put the result into the adder, and after you run 4 cycles, you are going to get the multiplication result, right? So that's a basic idea of shift and add multiplier. So right now, the question, right now, the question that I would like to invite you to think about is, well, okay, sorry, a little bit faster. So if you look at the circuit, right? So Right now, well, actually, I'm right. So right now, I would like to invite you to think about is that for this circuit, uh, okay, no, that's not this one. Okay, so for this multiplier, right? If we count the number of delays, right? So if we look at the circuit, right, the 8-bit adder is basically 5 gate delays, and the shift left is four gate delays, and the mux we learned before is about like two gate delay, and accessing a register is about 2 gate delays with the optimized register uh, um, um, organization, and writing the result is about like register of the product, right? And the multiplier is about 2 gate. So if you look at this, right? So the total number of cycles that you generate 1 bit result or one partial sum is not too bad. So right now, the question that I'm asking you is, if I want to evaluate the latency of a 32-bit say, okay, so right now, if I want to evaluate the 32-bit shift and add multiplier, so we just show you the 4-bit version. So right now, what if the 32-bit serial shift and add multiplier? What's the critical path of the circuit? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so let's look at what you guys think. So from the result, well, let's look at that. So 41% of you think it's B, and then D, C, and every answer has its own advocator. So I really need someone to tell me what do you think, and share your thoughts with us so that it would help you and your classmates in clarify those misconceptions that you might make in a final and in the future. So, okay, so I have Fox. Other people than Fox? Oh, come on. This is not a class of Fox, right? So can we have someone else as well? I mean, I love Fox, but I also love our other students, right? Okay, I guess I have no choice. Okay, Fox, what do you think?
Hello, can you hear me?
Hello, yeah, I can hear you.
All right. Well, so first things first, I'm going to look at all of the paths given and determine which paths even qualify for being a critical
Mm-hmm.
path. So,
Right. But
um,
before that, since you are here, right? And
right.
I know we are good friends. So if you don't mind, let me go back to this slide, right? So
Okay.
can we read out the red part of the sentence?
The clock's period must be longer than the longest delay from the state register's output to the state register's input, known as the critical path.
Right. So
Basically, the critical.
that's the critical path, right? So if you look at this, right? So uh, which path? How many paths are qualified as um, the path between state registers?
Well, they have to start and end at a state register. Doesn't have to be the
Right.
same one, but it has to start and end at one.
Right. So then which one is qualified? Which one is not qualified?
Well, let's see. A goes from multiplier to multiplier, so it qualifies. B goes from
Mm-hmm.
multiplicand to a product register, so that's fine.
Mm-hmm.
C goes from
Mm-hmm.
project register to project register, so it's fine. D goes from the
Mm-hmm.
multiplier to the project to the 64-bit adder, so it doesn't qualify. And then
Right.
E goes from the 32-bit shift left to the 32-bit shift left, so it also doesn't count.
Right. So this two doesn't count, right?
Right.
So now between A, B, C, how do I decide what is the critical path?
Well, let's list the components for each critical path.
Right. Okay.
So for A, we just have a 32-bit shift left.
Mm-hmm.
For B, we have a 32-bit shift left, a mux, and a 64-bit
Mm-hmm.
adder. And then
Mm-hmm.
for C, we just have a 64-bit adder. So
Mm-hmm.
what path has the most components in the way? B.
So so let me clarify one thing, right? It's not decided by the number of components, but actually the delay on
Right,
this
the delay.
component.
And this in this case, because B has all the components that A and C have, you can make
Mm-hmm.
the assertion that B must be longer than A or C. Um,
Right.
so or sorry, A and C.
Right.
Then that's the justification for the answer. But yes, if you also in cases where let's say it's one path has a component X and the other has a component Y, and there's no immediate way to know, you kind of have to take a look at both components to see which path's shorter.
Right. So the reason why B is the longest one is because like, well, here we have a 33 gate delays on the 64-bit adder. We have the shift left by 4, and we have the register we have to access by 2, right? And on the other hand, for the multiplier side, that the 32-bit shift to right only takes 4 cycles. However, if this is something else that takes longer than 33 cycles, then the answer might change, right? But you get it right, is that the critical path is this one. So you can imagine for a 32-bit shift and add multiplier, the gate delay is about 41 gate delays. Okay, so knowing the gate delay thanks Fox for your answer, and knowing the gate delay of the shift and add multiplier, why don't we spend time looking at this question? So if I am curious about like how long is it take to get my result for a multiply operation, which turns out to be the most efficient. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so let's look at what you guys think. So for the latency of multipliers, this is what you guys think. So looks like C is the most popular answer. So okay, so right now, before we announce the answer, let me ask you one more question. So what if we talk about if we are multiplying millions, 2 million pairs of 32-bit numbers? Oh, so this one should be pipelined 32-bit serial shift and add multiplier. Okay, Fox, do you have questions?
Oh yeah, I was just the poll window came up twice, and I answered it twice, both different answers. Or was I supposed to do that? I was confused.
Yeah, we are having 2 questions right now. We have one question on a pair of number, the other question on 2 million pairs of numbers.
Gotcha.
Okay, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so for this question, the answer looks like C is the most popular one. So let's go. So after thinking about this, right? So let's go back. Let's go back. I want you to read this. I want you to read this question carefully and tell me what do you think now. So that's the previous result showing. So what do you think now for this question again? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so after this run, well, the answer changes a little bit, right? So it used to be like C is dominating the answer of this question, and right now more of you think it's B. But which one is the right answer, right? Can I have someone sharing why you change your mind or why you don't change your mind? Sharing your thoughts with everyone. If I am adding two numbers, a pair of numbers, which multiplier would give us the best performance? I feel like I must put this kind of question in a final, and I would ask you why. So it's better that if somebody can tell us why and we know what the right answer is. And I would do exactly the same if somebody other than Fox is willing to share your mind. If not, then I will probably not even, I will probably design a more difficult question than that. And you don't know whether your answer is right or not. But if some of you now are willing to share your mind, I will put exactly the same question. Okay, finally. Giovanni, thanks for saving everyone. You are unmuted. So what do you think?
I think it was A because from previously that circuit we were doing where we're trying to find the critical.
Mm-hmm.
When we're going through that, I remember if the least amount is not the critical. So I was thinking, so the shortest end to end latency was the 32-bit shift and add multiplier.
Okay, so let's look at the design of 32-bit shift and end, right? So this is a 32-bit shift and end. However, this is just part of it, right? So for this 32-bit shift and end, okay, I think I have to modify this part of the circuit a little bit. So this is not, so this is 32, this is 32, this is 32. So everything here should be modified as 32. So for this 32-bit shift and end adder, we need a total of we need 32 of this guys, right? So how much delay we have to spend in one of this? Can you tell me? Like for this mux, how many gate delays? This mux.
Oh, this mux?
Yeah. Or in general, what's the gate delay for every mux? Okay, I have Nicholas. Okay, what do you think?
It's 2 gate delays per mux.
Okay, and how about this adder?
For 64-bit adder.
Mm-hmm.
Uh,
Any of
32,
you know the
I think
result?
it's 32.
32?
Is it
Giovanni?
32?
What do you think? Woohoo. Okay, so for the adder, right, we said for a carry lookup adder, it's n divided by 4 times 2 plus 1, right? So for this one, right, then it's 64 divided by 4. So it's actually 32 for the carry lookup head part and 1 bit for the SI, right? So this is 33, but you're not too far away from it. How about a shifter?
For a shifter. Okay. I believe, isn't it around 32 as well? Or is it 16?
Well, so basically, if you remember what we have learned in the previous lecture, right? How do we make the shifter? Like, what's a basic component inside a shifter?
I think it is 16, now that I think about it.
Okay, other people know the answers? Other people knows the answer.
If
Otherwise,
anyone would like to help me, because I
yeah,
feel like
help
if I just
him.
because I'm just gonna start speaking out. I mean, honestly, I'm gonna be honest. I'm not very knowledgeable. I'm still trying to pick pick
Yeah,
all
that's
this up.
fine. No one is very knowledgeable here, right? That's
So
okay.
I think I'm
And
just
I
gonna
would
try to
rather you
answer
get,
questions.
okay, that's okay. So, but right now I want you to remember. So do you remember what do you have in mind about shifter? What shifter is made up with?
I forgot.
You forgot, okay? So if you, okay, so Fox, okay, you're the hero.
Shifters are basically just muxes that reassign the
Right.
various bits.
Right. So, and we also, if we want to make it a generic shifter, right, we just need another mux, right? So in this way, what's the total gate delay for this kind of generic shifter?
It's gonna be 2 muxes.
Yeah, 2
One
muxes. So,
one two input mux and one mux with the input count being however many places you want to be able to shift.
right. So then that's the how many gate delays in total?
4, 5,
Yep. Right.
4.
So 4. So you can think about that, right? So for this adders is 32, 33. For shifter is 4. For the mux is 2, right? So every part of this adder requires this. So it turns out that we need this amount times well, I think we have to do if we have to do 32-bit shift, it's actually it's 39 times 32 gate delays, right? So that's the amount of gate delays we are suffering, right? So in this case, if we go back to this question, right? Go back to this question. For the 32-bit shift and add, right? We say it's 39 times 32. So how about the array style? We already say it's AOA, right? How about the pipeline 4-bit serial and add multiplier? Do you have anything in mind for Fox?
Oh, for this one, hold on, can you go back to the last slide? Because these few slides, it seemed like the answers were changing based on the slide, even if the question wasn't.
Okay, this is the slide. This is a 32-bit, right?
Oh, okay, maybe that's just my eyes. All right.
Right, and the other is this one, right? So that's the serial adder, right? So
Right.
for the stereo adder, it's this, right?
No, I remember there were two
41.
versions. There were two versions of the question, and you also
Right,
changed the question.
right. This is the yeah. And there is a purpose for this question, right? So if you look at this question, right, it's talking about end-to-end latency in multiplying two numbers, right?
Right. Yes.
So if I want to measure the time of multiplying two numbers, right, it's the beginning when a number enters this pipeline or the multiplier till the end of the result of these two numbers is generated, right?
Right.
So for pipeline 32-bit serial shift and add multiplier, right?
Oh,
Well,
it
we
is
said
32-bit. Right. Okay.
right,
Yeah.
then it's 41 times 32, right? So if you look at this, right, first of all, C is definitely longer than A, right? And if you count it, this is around 40. This is more than 30, right? So you know this is more than 1200. So so B is actually the shortest one, right? So for this question, if we are just talking about two numbers, right, we are talking about the end-to-end latency. Okay, Nicholas, question?
Yeah, I'm sorry. I'm still kind of confused how you got 39 times 32 and 41 times 32.
So how do I get this, right? So for the case of 32-bit serial multiplier, right? you need 32 copies of these guys, right? You need to duplicate this part of the circuits for 32 times.
Oh, okay.
Right? So that's how you get 32 times 39 because each part is 39, right? And for the stereo version, which we already talked about, right? And I encourage you to think what's the critical path of it, right? So the inner part is basically the same. So this part is still about so this part, I think, is basically the same as the serial version. However, you have to add. So this part, if you look at that carefully, is 39. However, because this is the serial version, so you always require a register to buffer your intermediate result. So it turns out that you get two more gate delays here. All right. So then it's 41 gate delays, right? So if you look at the latency of this multiplier, and here I made a typo, it's 32, right? Then the total number of gate delays is like this. Is that clear now?
Yeah, that's perfectly clear. Thank you.
Okay, so thanks, Fox, and thanks, Nicholas. So I hope everyone is clear about the definition of latency. So when we reading carefully, right? If we are just talking about two numbers, multiplying two numbers, it's the beginning when we receive the two numbers and the end of generating the result. So these two numbers, they must go through all the gates required to generate the result. And for the pipeline version, you have to go to 32 stages. And the pipeline version is actually nothing different from the first one, except that for the pipeline version, we have to insert those serial pipeline register in there. So it turns out that the gate delay is 2 cycle more, or say 2 nanoseconds more in this case. So the latency of getting those numbers is actually the best for B. However, A is slightly better because you don't have to suffer from the overhead of pipeline register. And for C, is the worst for end-to-end latency. But how about, what if we talk about the throughput? Then if we talk about the throughput, right? So this made a few typos here because I'm modifying this question from the editors essentially. But if we talk about 2 million pairs of 32-bit numbers, then what you should imagine is that a graph like this, right? So if it's a 32, if you have tons of them, right? If you have if you just have combinational circuits, right? The combinational circuit saying that if we have a shift and add, it's basically saying that I am doing first, second, third, fourth, and only after I finish a number, I can start the next chunk of the first, second, third, and fourth, right? So that's the non-pipeline version. So in this way, you can think about whoever has the highest frequency will give you the best performance. And the answer is definitely the answer is definitely the pipeline version, right? So that's the biggest difference. So pipeline is a good idea if you are dealing with a huge amount of operations, which in our modern computers, in our modern design, that's true. However, that's not the case for if you are just dealing with one number. Okay, Fox, what do you want to say?
Okay, this is actually slightly unrelated, but the Cray supercomputer, also known as the Couch supercomputer, was a pipelined supercomputer that would basically perform a lot of operations at the same time, and it worked really well. And the secret to that was, instead of using any register buffers, for every single compute circuit, they were connected with wires of the same length. And they use the time delay of the signal propagating through the wires as a form of memory. And they would just pump a higher frequency of data through those wires than they actually could store.
Yeah, so that's another way of doing it, right? But,
yeah, but
the the overhead of that is pretty, I mean, the circuit overhead of that is pretty high. So we probably won't do that in
No, we wouldn't do
a
that
single chip
now.
design. Yeah.
But that was the method they found back then. I thought that was actually really neat because that was a demonstrable form of pipelined computing,
Right.
and how they took advantage of it.
Okay. All right. So thanks for your comment. So right now, I believe through this question, you should have a basic idea of what's the difference between throughput and latency. When we talk about latency, it's talking about how much time we spend in each pair of the numbers, right? So each pair, if I'm just only asking about each pair, right? The individual end-to-end latency of each pair within this 2 million numbers, then the answer would be B. However, if right now I'm talking about generating result for the total 2 million pairs of numbers, then this is definitely the result that we are looking for, the one that we are looking for. So that's why most all your processor right now are pipeline because of that. Because when you are running a program, you are dealing with thousands, millions of instructions, not just one instruction. So we would like to have pipeline design in our modern microprocessor controller or everywhere, or signal processing, everywhere we want to deal with a huge amount of inputs. All right, so after introducing the register, after introducing the shifter, after introducing the adders, after introducing the multipliers, we have learned important data path components that could help us to design a microprocessor and accomplish basic operations. And the issue is that the processor has only one clock generator, and each data path component has a different latency. How can we make, and we have to make some of the above serial, but even though we have to make some of the above serial, for the multiplier, we probably need 32 stages in a pipeline. For the shifter, we don't, it's pretty fast. For the register, it's pretty fast. And for the adders, it's faster than the multiplier. So the question comes back to this: how do we control a combined design with elements with various latencies? So before we talk about how to realize that design, we have to talk about a new concept called high-level state machine, which I believe you guys already learned it from the reading quiz. So so let me give you a short recap of a short let's drift away from the microprocessor example a little bit. So let's talk about the soda machine, which we are not able to access recently on campus, but you must remember there are quite a few of them on campus. So for the soda machine, right? Basically, we receive a few inputs. We have okay, so I think one arrow is not correct here. So we receive the input like if we have coin, right? And we have another input which is like how much we deposit and the cost of the soda. And let's see if you have given the machine sufficient amount of money. So if that's true, then we can dispense a soda for you. So that's a basic idea of high-level state machine for soda. So that's the basic idea of a high-level state machine. Sorry, for a soda dispenser. So we want to use this example to talk about what the high-level state machine looks like. But before we talk about, I know you guys have already done your reading quiz. So what if we use this question to test by how much you understand the difference between high-level state machine and a general state machine? Let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so let's look at what do you guys think? So we have two very popular answers, both A and D. So can I have someone explaining what's the difference between high-level state machine and finite state machine? They are all state machines, but what's the difference between the two state machines according to what you just learned from the textbook? Okay, so I have Fan Zhong, Li. What do you think?
I picked A because um because I just thought, well, Zybook said so. So
Zybook says so. Okay,
well,
yeah. So
honestly,
that's an answer, right? So
Right.
because Zybook tells you that, right? But how about the other two? Why they are not correct?
So I think high-level state machine, it says that it's basically finite state machine with multiple data bits.
Okay, but
So
how
it
about
does-
the other
does
two?
store states too. So it works just like a
Okay.
finite state machine, but with more data bits.
Okay,
That's my
so
understanding.
okay, Fox, what do you think?
Well, I mean, I think B and C are misleading statements or just outright false. It's just that finite state
But
machine.
in what ways they are misleading?
Well, so finite state machine, it stores a discrete number of states as data. But the high level state machine is variable data, but we still represent the high level state machine as various states and with
So you still
with
need
data
states,
fields.
right?
You still need states. And
Right.
actually
Right?
all
because
high
they are all state machines, right? So they
Right.
need state.
And all high-level state machines decompose to a finite state machine. It's just if you drew them as finite state machines, they'd be basically illegible. Because like our multi-bit data fields, you could just write truth tables for everything. It's just the truth tables would be way too long to even print. That's why we don't
Right.
use finite state machines in these scenarios, because we're handling too much information to represent every single last combination. We got to start grouping things logically.
Okay, so how about the third one?
Well, I mean, a finite state machine doesn't even require more than one bit register, I guess, technically. But saying that statement is like saying nothing at all, because again, in implementation, they look kind of similar.
Right. So the thing is that you are right. The high-level state machine is just an easier way to represent a very complex case for the system design. And and finite state machine, as you said, in some cases, the finite state machine doesn't require multi-bit data registers to implement. However, for high-level state machine, because that's the purpose, right? The high-level state machine want multi-bit data. So we require multi-bit data registers, but that's not a requirement for finite state machine. And in fact, when we are talking about the finite state machine, the example that we show you is always about like 1 bit output, 1 bit input. And if we want multiple bit, we will separate them into different flip-flops. So that's another indication that finite state machine doesn't have the requirement of multi-bit data registers. Okay, so thanks for your comment. So, but right now, right, so that's the difference between finite state machine and so the answer for this question is actually A, because that's some of you said it's a Zybook thing that stores multi-bit data, and B and C, they are not true in a way that every state machine, if it's a state machine, you have to save the state somewhere. And multi-bit data register is not a must for a finite state machine. So right now, let's look at this one. This is even simpler, right? So how are they the same?
What do you mean by external complex data?
External complex data means that you have complex input. Like your input could be multi-bits or something.
Oh, okay.
Okay, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so let's look at what you guys think. Whoa, we have 2 questions in Thai, A and C. Why 2 answers in Thai? So can some of you share your thoughts about this? Like, so the biggest disagreement here is B, right? What is B correct or not? Is B correct or not? I imagine this should be something fresh in your mind, right? Because you just learned it. Okay, Nicholas, what do you think? You put your hand down. Okay, so Nicholas, hello. Do you want to say something?
Yeah. Originally I chose C, but after you clarified what the external complex data is, I actually believe it's just A.
Okay, but why not B?
Because FSMs don't store multi-bits.
Okay, so this is talking about like external complex data, right? So it means that are we accepting those multi-bit input and some of the complex input here, right? So so for the high-level state machine, why we want them? Why we want them? So let's look at the definition of the high-level state machine, right? So it's actually an extension a finite state machine with multi-bit input output, which in our finite state machine, there's only one bit output. And the other thing is that we extend it with local storage. So you could have some kind of like data storage in there. And the convention is that each transition is implicitly ended and with a rising edge of the clock, which is the same as your finite state machine. However, for multi-bit outputs, that's something the finite state machine doesn't have. And every high-level state machine output is registered. Okay, Fox, do you have anything that you want to add? Okay.
Yeah, I wanted to add that state and stored data are fundamentally both information. They're both stored as flip-flops information. States are just enumerated in a table, and then the synthesizer will just figure out the best ones, or you can by hand. But ultimately, like the reason why I say HLSMs decompose to FSMs is because if you were to just look at the gates themselves, it's actually kind of hard to tell the difference between the storage registers and the state registers.
Okay, so let me ask you one thing, right? Okay, that's something that I forgot to mention. So in this high-level state machine, what's the storage? What's the state? Who are the state? Who are the store? Who is the storage?
So we have our 4 states, add weight, init, and disp.
Okay, so they are states, right? So for those states, we use flip-flop, just a single set of flip-flops to represent them, right? Who is the local storage? Or, yeah.
So it looks like we
Actually,
have a total.
who are the locals? The total, right? It's a variable, right? Your total value can change. And this is the most significant difference between high-level state machine and a finite state machine, in a way that finite state machine only have this init weight at display, right? And if it doesn't have the ability for local storage like total, right? You can never say that, well, I have a local storage, right? You don't have the local storage, right? It's only state transitions. However, that's not the case for high-level state machines.
Yeah, the problem comes out that if you were to try to like represent even like a 2-bit variable using a finite state machine, you could kind of do it, but you'd end up with a lot of extra states that you can't collapse. And it's just, it's not feasible to represent it that way.
Yep. Okay. Anything else you want to add? Okay. So high-level state machine, right? We have the local storage, which is not existing in the finite state machine. And the other thing which you look at that is that if you look at the state transition diagram, right? Your state transition can have more complex scenario that you not only have the signal of C, you are also tell the signal of S, right? Which in our finite state machine, we only transition the state based on a single input, right? That's also something that is different from finite state machine to high-level state machine, is that our input output can be multi-bit, and they can transit their states based on different signals. However, that's not a capability, or say not the standardized form for finite state machine in our textbook. So this is the biggest difference of high-level state machine. And because you can have data, you can have control, and they can be multi-bit. So that's why we call this complex data structure. But if you try to remember what's going on in your finite state machine, when we transit, it's always like C or C prime, instead of like C is smaller than this number or something, right? So this is the high-level state machine representation. So for the high-level state machine representation, right, then it tends the finite state machine with this, and there are some conventions. So if we want to represent a single bit number, you use the single quote, and if you want to represent multi-bit number, you use a double quote, and you can also use no quote to represent integer, and you could have if you want to say, well, this is equal to what, you use double equal, and if you have multi-bit output, it's going through the local storage. So that's the high-level state machine representation. And for this soda dispenser, right? Let's look at this. So the high-level state machine of the soda dispenser looks like this. In the very beginning, when you face on it, right? You didn't do anything with it. So the total number that you put in there is 0. And we don't dispense anything for you, so it's 0, right? And then wait a little bit, and it transits to another cycle. That's the initialization. And then you transit to the next cycle, which is the ready state that we are ready to accept your coins. And then for the ready state, if someone is depositing a coin, then it goes to the F state. And what the F state would do here is that we will calculate, we will update the total number equal to be total plus A, which is the number of the value of coin that you deposit. And let's go back to the wait state. And if the C prime and the total is smaller than S, then and if both of them are not true, right? If both of them are not true, means that you already got sufficient amount of money in there because your total is actually greater than S. So we can dispense the stuff for you and give you the stuff that you need. So that's the high level state machine for the solar dispenser. And if that's not the case, meaning that right now, if I'm not putting a coin and the total that you put is still smaller than the total amount of money that you should give to retrieve that soda, then let's stay at wait and see if the user is giving us more money in that. So you can definitely do this using finite state machine, but remember, right? If you just want to do it with finite state machine, then first of all, this scenario you have to handle it in a different way because that's not allowed in finite state machine. And for the A, you have to deal with that differently because that's also not part of a finite state machine. So that's why we try to put everything together in high-level state machine. So that's the basic concept of the high-level state machine. You should be able to find this example on Zybook or similar example on Zybooks. So knowing the concept of high-level state machine, let's talk about the RTL design. So the RTL design is actually, or say the register transfer level design is actually giving you a high-level system view of the design. So as we said, right, high-level state machine can help us better capture complex behavior of the total circuit. So if you want to realize your intended design into a system design, then what you really need, first of all, you need to capture a high-level state machine, HLSM design. So to make that happen, right, here's the recommendation. List all inputs, outputs, and local registers on top of your high-level state machine diagram. And so like the soda dispenser example, right? First of all, you have to draw something like this. Okay, I want to draw a black box of soda dispenser, and I need to have this input and I need to have this output, right? So this is the first step. And then thinking about their interaction, you can draw the state transitions, right? And for each transition, you have to on each transition, you have to remember what are the conditions that would force us to transit to a different state. And for each state, we are updating the value of register, updating the outputs. So this is the first step. So if you want to do a system design of your circuit, first of all, try to draw a high-level state machine. And the step of drawing a good high-level state machine first, list all inputs and figure out what's the size of each of the inputs, output, and local storage. And for each state, update the value of registers, update the outputs, and express conditions in terms of a high-level state machine inputs and the arithmetic operation between them. And then we need to convert it to a circuit. So to convert the high-level state machine to the circuit, as we said, high-level state machine is something with local storage. So that's why we talk about memory. That's why we talk about registers. So for the data path components, right, you need memory, registers, and we have arithmetic operations. So you need those comparators, which we also talked about in the past. And if you want to do add, you need adders, right? And if you do want to shift, you need shifter. So we have talked about all of this, right? So these are the elements that we have talked about. That's why we spend so much time talking about this data path components, because if you want to do a system design, they are essential. And then connect the data path to a controller, which we didn't talk that much about. So for the high-level state machine, is the state machine describe the state transition of the controller and how we define the behavior of each data path element at any given moment, right? So that's the second stage. So first of all, you have to think, if I want to implement this circuit, what are data path components that I need? And then try to create a controller and then derive the controller's finite state machine, right? And so that's why we still need to teach you finite state machine first, because the high-level state machine end up breaking down into finite state machines in your controller. And the final step in implementing that is to put them into the logic. So here's a summary. So first of all, if the RTL design summary is just like this: capture the behavior of a high-level state machine, and then convert it to a circuit. And then for the circuit part, we need to have the high-level architecture, data path, control path, and data path capable of the data operations and design controller to control the data path. So let's say I am creating data paths for a soda dispenser, right? So for this soda dispenser, this is the high-level state machine we have. And we know for this, I have 4 different states, right? So I need a register or say some kind of flip-flop to maintain these 4 states. And this part is covered by the state machine, right? However, what the other components that I need here is that for the total, I need an A-bit. I need an A-bit register to store the value. And for here, I need an adder to perform the total plus A. And here, I need a comparator to see if I'm currently smaller than S. So these are the data path components that we need for the soda dispenser. So you can imagine if I want to create the data path for the soda dispenser, here's what I need. I would need at least an 8-bit adder. I need a total register, which additionally could give 2 functions, like you can put a value in here or you can clear the value in here. You also need a comparator. And these are their inputs, like and outputs, right? So this is essentially what you need to realize the soda dispenser. And so those are the data path components. Then and then the next thing that we need to do is about how to design their controller, right? So let's see. Well, I do have some more slides on the controller, but because I think we are short on time, so let me go to somewhere first. Some other things first. So last lecture, when I talk about that, we have to you have to pay attention to materials not on a textbook, because you guys are aware that you got the Zybook for free. And although the Zybook says it's digital design and it's also written by Frank Bahid, but the truth is that if you compare the second edition book and the Zybook, the content is actually a lot less on the Zybook. And the reason why I don't use Zybook, I don't use the physical book is, first of all, even for a used book, it's this expensive. And the new one is also about like 120 bucks. And so that's too expensive. Plus, we know we have the COVID-19 period of time that the Amazon is not giving not shipping stuff on time. So I want to avoid this kind of chaos. So that's why we chose to use Zybook Plus. It's free for us. However, the cost of that is that there are tons of stuff not covered by the Zybook. So that's why I have to make slides out of those materials that are missing in the Zybook. And those materials, they are very important. And when I made those materials, I actually referenced what has been taught on other UC Riverside sessions, and also some materials from UC San Diego and MIT. So we do have some materials that other UCR sessions are not covering, but stuff that's covered by some other school. And the reason is because you have to realize one thing: when you graduate, you are competing with every computer scientist, electrical engineers all over the world. So if they knew this, if you have to know this. It's not about the fairness among within UC Riverside. It's about how can we better prepare you for your future. Okay, Fox, anything?
Yeah. Is this textbook used in any other courses?
This textbook is used by only 120A, I believe.
What is one? Oh, so 120B doesn't cover something completely
Yeah,
different.
it's a different class. Yeah.
All right.
Okay. Okay, so this is and that's the reason why in the final I mentioned that there are tons of materials missing in the Zybook, and I have to add this in in our lecture slide. So please pay attention to that. And a lot of stop the music. Okay, so
Yeah, actually, your music has been drowning out your like end of lecture announcements, like every
Okay.
other lecture for a while now.
Okay. So so first of all, for iEval, right? I encourage you to take that iEval. So what you need to do is that you capture your screenshot and send it on iLearn. Don't send me in an email. I already see a few emails. I don't want to see the email. I want to see your submission in iLearn. The reason is because it's easier for me to input your grade. And the thing is that we value your comments, and also try to consider that this is a very difficult period of time, and we have made sufficient amount of effort in making this class go on and working, like in the very beginning of the Zoom bombing stuff that I know it creates a lot of issues later on, but that's the only choice we have. Another thing, the last item, final exam will be held during the campus schedule period to avoid any potential conflicts. And so the time will be June 11th, 11:30 a.m. To 2:59:59. So that's the time for the final exam. Make sure that you are free at that time, and it's about the same format as the midterm, also through iLearn, but it's a longer exam, means that we are going to have more questions. Other than that, I'll enjoy the rest.